All right, so today's physics lesson is about refraction. There's a lot going on in this video, so do the best you can with it. I really think this is one of those videos where it might not be a bad idea to watch it twice, despite the fact that it's really long. And obviously we'll spend a ton of time on this in class to, to ensure that everybody understands what's going on. All right, so we're going to learn about refraction today. Today we're going to focus solely on problems where the light changes medium, so it's going to go from one substance to another, like from air to glass, or water to glass, or whatever. And that change in medium is going to cause the light to slow down. Okay, so our light's going to go from a medium where it travels fast to a medium where it travels slow. And then in the next video we'll talk about the other side of that, if it goes from, if it speeds up, if it goes from slow to fast. Okay, so here we go. First of all, you need to know what the index of refraction is. The symbol for index of refraction is a lowercase letter n. So here's the deal with index of refraction. So before we get into it, you need to remember that the speed of light, or really any wave, is determined by the medium that it travels through. All right, so the speed of light in a vacuum is 3 × 10⁸ meters a second. The speed of light in air is basically the same thing. It's a teeny bit less, technically, a teeny bit less than this, but so close that you can treat it as the same thing. All right, speed of light in water is this number, 2.25 × 10⁸. And what you should notice is the denser the medium is, the slower the light goes. All right. Also worth noting, this number here has a special name. That number is called the speed of light and is abbreviated with the lowercase letter c. So from now on, whenever you see the letter c in an equation, that means 3 × 10⁸ meters per second. That is the speed of light in a vacuum. Okay, so even in Einstein's E = mc² equation, which you may have seen or heard of, that is what c is, 3 × 10⁸ meters per second. Okay, so the speed of light is determined by the medium it travels through. Now, every medium that light can travel through has its own what's called index of refraction. Okay, the index of refraction is calculated by taking the speed of light in a vacuum and dividing it by the speed of light in your medium. So, for example, suppose I gave you some sort of new gem, and I told you that the speed of light in that gem was 1.5 × 10⁸ meters a second. So what we know is the velocity of light through this gem is 1.5 × 10⁸ meters per second. So to find the index of refraction for this gem, we would take c and divide it by the velocity of light in the gem, which is 3 × 10⁸ meters per second divided by 1.5 × 10⁸ meters per second, and it gives us 2. Notice there are no units because the meters per second cancel there and there, so you do in fact just get 2. That number means something though, so here's what that number means. So what that number means is that the speed of light in a vacuum is 2 times bigger than it is in the gem. Okay? So it is basically just a ratio. Sometimes people will refer to it as sort of optical density. The idea is as your medium becomes denser, your index of refraction goes up, which can be seen here, where I've gone through and calculated the index of refraction for a couple different mediums. So the index of refraction for a vacuum is 1. The index of refraction for air is so close to 1 that we're going to call it 1. For water, it's 1.3. For glass, it's about 1.5. It depends on the type of glass. For diamond, it's about 2.42. The only numbers here you must have memorized are these guys. You're going to need to know the speed of light in a vacuum. You're going to need to know the index of refraction for a diamond, or for a vacuum is 1, and for air, it's 1. You should also please know that, I hope you can read this on your screen, it says the denser the medium is, the slower the light goes, and the higher the index of refraction is. The denser the medium is, the slower the light goes, and the higher the index of refraction is. Okay? So that is what the index of refraction is. The higher the index is, the slower the light goes. All right, so on with refraction. Anytime a wave travels from one medium to another, and I don't know if you can tell, but this is bold, anytime a wave travels from one medium to another, a couple things happen. First of all, some of the wave will reflect, in other words, bounce back into the original medium. Okay? And then some of the energy that doesn't reflect will move into the new medium. This change in medium causes the wave to change speed, and depending on how the wave enters the new medium, it could cause the wave to refract. All right, so in the same way that reflect is a fancy word for bounce, refract is a fancy word for bend. All right, so depending on how the light enters the new medium, it could bend, could refract. So we should briefly talk about why this happens. So here we go with the dune buggy example, although I didn't have a dune buggy, so I used a car. So here's what I'd like you to imagine. I would like you to imagine a parking lot. So here are some parking spaces. This car is going to do a terrible job parking. All right, so this, where I'm drawing my lines here, represents our parking lot. And then down here is beach. Okay, so let me erase all that. That was dumb. All right, sorry, fail. All right, so there we go. So what's going to happen is our car is going to drive from a parking lot to a sandy beach. And the idea is it's pretty easy for a car to drive on a parking lot. So this would be a medium in which our object is able to travel fast. It would be analogous to a very low index of refraction, okay, because our object is able to go fast through it. Now, a sandy beach, the car is going to go slower on a sandy beach. So that would be like having a high index of refraction. Okay, so what's going to happen is this. If the car just drives straight down across the parking lot and onto the beach, what's going to happen is, boom, it hits the sand and it slows down, right? So it's going, whatever, 40 miles an hour, 40 miles an hour, 40 miles an hour, 40 miles an hour, boom, 20 miles an hour, 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 right? Okay, and there was nothing weird there. The car just kind of goes straight through and it slows down as soon as it hits the beach, all right? But what happens if the car goes in at an angle? What happens if the car goes like this? Then it's going to go, you got to make the sound effect, and bam, right there what happens is this first wheel hits the sand, and it causes that wheel to slow down, but the other one still goes faster. So what ends up happening is the car comes in like this, but as soon as it hits the sand, it causes it to rotate a little bit. All right, and unfortunately I can't get this to rotate exactly the way I want it to, but basically this corner of the car slows down and the other keeps going faster, and it causes the car to pivot so that it, instead of just going straight through this way, it bends and goes this way. So the car is going to go this way, then when it hits the sand, it turns and goes this way. All right, light refracts for the same reason. It's caused by the change in speed as it goes from our first medium to our second medium. And this idea that I've got drawn here is going to be huge. This line here is what we're going to call the boundary between our two mediums, two media. So every time we make a drawing, we're going to start with that boundary, okay? And then we'll talk about how the light bends. All right, so now we need to talk about sort of how to predict how much the light bends when it goes from one medium to another. So reflection is easy. We just use the law of reflection. You guys already know this, right? That if your beam of light comes in like this, it's going to bounce out like this, so that your angle of incidence equals your angle of reflection. Okay? To calculate the angle of refraction is a little bit tougher. You actually have to use what's called Snell's law. So to do that, you need to know your two indexes of refraction. This is n for the medium on the incident side. In other words, whatever your beam of light is starting in. And then this is on the refracted side, whatever the light's going into. Okay, and then there's two angles. This is your angle of incidence, which you already know. This is your angle of refraction. All right, it is worth noting that there are now three angles. There is angle of incidence, angle of reflection is RE, and angle of refraction is RA. That says RA. Okay. So let me show you an example of refraction, and then I'll sort of show you what all the different variables are. Okay. Okay. So what we've got here is a laser beam. Our laser beam is starting out in air. So the index of refraction for air, like we said before, is 1. And down here at the bottom, we've got glass. Like I said, N for glass varies depending on the type of glass, but let's just assume that it's 1.50. All right. Now, so this line here represents the boundary between the two substances. All right, and we're going to have an incident beam that's going to come from this laser over here. And so this dotted line here is already drawn in. That's going to be our normal line. Notice it is perpendicular to the boundary. All right, so I'm going to turn on the laser. Oh, no, I'm not. Try that again. Turn on the laser. All right, and what you'll notice here is there are 3 beams of light. There is our incident beam, where this is your angle of incidence. The beam comes in this way and reflects this way. So this is our reflected beam. So here is our angle of reflection. Now we can use our, law of reflection and make sure that our angle of incidence equals our angle of reflection. And this is actually a cool protractor because it's got 0 at the top instead of on the ends. Wish you could buy these. So what we can see here is our angle of incidence is cluttered and tough to measure. It looks like it's about 45 degrees, right? 10, 20, 30, 45. And over here our angle of reflection is 10, 20, 30, 45 degrees. So our angle of incidence does in fact equal our angle of reflection. All right, and then there's this third beam, which is this guy. Oh no, I dropped the microphone. So there's this other beam here. This is our refracted beam. Notice it traveled into the glass, but it bent. It didn't keep going in a straight line this way. It bent, what we say is toward the normal. I'll talk about that more later on. So what we need to figure out is this angle of refraction, and that is what Snell's law tells us. All right. All right, so the one other thing then I guess worth commenting on is, so we talked about our different angles. There's angle of incidence, angle of reflection, angle of refraction. There's also 2 n's, right? So Ni is the index of refraction on the incident side. My beam in this example is starting in air, so my Ni is N for air. And then the beam of light goes into glass, it refracts into the glass, so that would be my Nra. Cool? No affiliation with the organization of the same initials. All right, so there are basically 2 types of examples that you're going to see. There's 4 variables here, right? There's 2 indexes, 2 n's, and 2 angles. Okay? So in every problem, you're going to know 3 of the 4. So either you're going to be missing an index or you're going to be missing an angle. So let's do an example of each. All right, so as a quick comment, if you want to use this program here, if you want to monkey around with it, which I do think is not a bad idea, if you go to Google, and you Google the word PHET and the word refraction, it'll be the first hit that comes up. So totally worth your time. All right, so anyway, moving on. So here's our example. So in this first example, we're going to learn how to find the index of refraction. Okay, so a beam of light travels through the air and strikes a piece of clear plastic. The angle of incidence is 55 degrees and the angle of refraction is 35 degrees. Find the index of refraction for the clear plastic. So you should start by making a drawing. Your drawing will always start out the same way. You're going to have a boundary. You've got a beam of light traveling from one substance to the other. So I'm going to always get in the habit of putting my incident beam on the top and my refracted beam on the bottom. So in this example, we're going through air and into plastic. So this is air. I know N for air is 1. And then we're refracting into plastic. And we're trying to find the index of refraction for plastic. So N equals question mark O. That's a question mark. Okay, so I am really unhappy with how wavy my boundary is. So let's try that again. Wow, I'm apparently pessimistic because it keeps going downhill. All right, let's see. So the beam of light is going to come through and hit the boundary. You can right away put in your normal line. The problem tells us that the angle of incidence is 55 degrees. So here's my angle of incidence, 55 degrees. Right away, I know there's going to be a reflected beam. So this is incident. This is reflected. Okay, and the beam of light, when it goes into the plastic, does not go straight. Don't draw this, but I'm about to draw in red. It doesn't do this. It bends and goes this way, so that my angle of refraction is 35 degrees. All right, and this red line was just meant to indicate what would have happened if the light had not bent. Okay? So, let's write down what we know. I'm going to add in a blank page. Here's what we know. We know our Ni is 1. We know our theta I is 55 degrees. We know our angle of refraction is 35 degrees. And we're looking for NRA because we're looking for N for plastic. So we can use Snell's law. And here we go. Ni sine theta I equals NRA sine theta RA. And plug in your numbers. 1 times the sine of 55 degrees equals x. If you prefer, you can use x times the sine of 35 degrees. And we got to solve it. So, all right, so all I did was I typed into my calculator sine of 55 to get 0.819 and sine of 35 to give 0.574. So now it's just algebra. Divide both sides by 0.574. Oops. And you get x equals, so that gives you 1.43. So that represents N for our, what were we looking at, glass? Plastic? I don't remember now what it was. I guess I should go back. Oh, it was plastic. N for plastic, this particular piece of plastic, is 1.43. All right. Now, what I didn't put in the question that I should probably point out, because it's something that you'll have to do from time to time, is this. Now that I know N for plastic, I can actually find the speed of light in plastic. So remember, this equation is important because it allows us to convert between N and V. So the idea is right now I know N for plastic is 1.43. So that's got to equal the speed of light in a vacuum divided by the velocity of light in plastic. So if you algebra your way through this, you end up getting, oops, you end up getting this. The velocity of light in plastic is 3 times 10 to the 8th meters a second divided by 1.43. And weirdly, this gives you, actually, there's nothing weird about the answer. Sorry, I was thinking it gave us something else. So in your calculator, it's going to give you 210062261.5 or something like that. But again, not again, but if you convert that into scientific notation, it gives you 2.1 times 10 to the 8th meters per second, which is the speed of light in the plastic. All right, if you need help converting to scientific notation, let me know. All right, so there we go. We have now done one problem where we found the index of refraction and then used that to find the speed of light in plastic. This equation here, I don't know if I said this already, I've had to pause this a couple times here, but this equation is huge because it allows us to convert between N and V and vice versa. So if you're solving a problem and I give you the velocity of light in a substance, you can use that to find N. And if you find N but need to know the velocity, then you can go that way too. Okay? All right. One last example. I know I'm going over my 20 minutes again. This section is pretty involved. All right. So for example 2, this time we're going to find an angle. All right. So this time it says a beam of light travels through the air and strikes a piece of glass. And I gave you N for the glass. It's 1.58. It says the incoming beam forms a 25-degree angle with the surface of the glass. And find the angle the refracted beam makes with the glass. So there is a lot going on here. All right. The first thing I want to caution you on is please be careful about the wording of the angles. All right, so here we go. Let's draw this. So we've got, here's our boundary. It's going through air. So up here we're going to have air where n is 1. And we're going into a piece of glass. And it tells us the n for this piece of glass is 1.58. Our beam of light is going to come in through the air. So this is our incident beam. Draw on your normal line. Now you got to be really careful when you measure these angles, because check it out. It says the incoming beam forms a 25-degree angle with the surface of the glass. So the incoming beam forms a 25-degree angle with the surface of the glass. So this angle here is 25 degrees. That isn't your angle of incidence. Your angle of incidence is actually this guy over here. So to find that angle of incidence, it's 90 minus 25. So it actually gives you 65 degrees for your angle of incidence. Please be careful about that. Okay, remember, any type of angle, whether it's theta I, theta RE, or theta RA, is an angle between a beam of light and your normal line. Okay, so let's kind of clean up the rest of this drawing here. All right, so we automatically know we're going to have a reflected beam that goes at the same 65 degrees. And we're trying to find the angle the refracted beam makes with the glass. So really, what we're going to do is we're going to find our theta RA and then use that to find this angle. Because again, we're looking for the angle between the refracted beam and the glass. All right, so pause the video here, read through the problem, and take a look at my drawing and make sure you understand what's going on there. And if not, that's definitely going to be something that you want to ask about when I see you in class tomorrow. All right, so we need to find our angle of refraction. So here we go. We're almost done. Ni is 1, theta I is 65 degrees, NRA is 1.58, theta RA is question mark. That is really sloppy. All right, here we go. Ni times the sine of theta I equals NRA times the sine of theta RA. And plug in your numbers. So you get 1 times the sine of 65 degrees equals 1.58 times the sine of theta RA. So solve it. So the sine of 65 is 0.906. That's going to equal 1.58 times the sine of theta. When you're doing a problem like this, get this mess by itself. Okay? So we're going to now divide both sides by 1.58 so that you get the sine of theta RA is 0.574. And so then to solve that, hopefully you know by now, you can take your inverse sine of that same number. And it should give you pretty close to 35 degrees. So let's go back to our drawing. That means that this guy here is 35 degrees, which means our question mark is 90 minus 35, which actually gives us 55 degrees. And there's the answer. Okay? So that's it. Snell's law. There's a lot going on there. Once you figure these out, though, there's only so much I can do here. So if you're frustrated right now and kind of going, what's going on, then come in, let's ask some questions. This is one of the hardest things we do this year. So don't stress about it, all right? Just if you are super confused, go back and watch the video again. I know it was long, but find some time to do that. All right? Have a good one.